Dear fellow Cosmology from Home 2022 attendees, greetings from Auckland, New Zealand. Today my presentation will be based on a recent PRD paper that discusses the nature of ultralight dark matter in the context of the dynamical friction effects it produces on a massive object traveling through it. I think most of us do not need much more motivation why dark matter plays an important role in our understanding of the universe today. For a theorist, a good dark matter model should be dark, shouldn't participate in E&M, should be stable enough to persist in large quantities in the modern universe, and should be cold, moving at non-relativistic speeds, and it may be leading to physics we don't yet understand. Last year, I made a map of a few corners from which people might pull particles or mechanisms that explains the unseen mass, the structure formation, a dark matter candidate. While this map might be getting out of date slightly, I think it's quite entertaining to watch, to read. And today, I'll be talking about the ultralight boson idea. It postulates that a very, very light scalar field is behind pulling the strings upon which galaxies and stars coalesced. This model is capable of generating similar large-scale features as the other dark matter models. However, within the galaxy, due to its large de Broglie wavelengths, the behavior is vastly different, and it even can be said ULDM exists as a Bose-Einstein condensate. There are a few astrophysical motivations as well. Most pertinently, ULDM solves the core Cusp problem, that observations of galaxies suggest the cores of galaxies should have a smooth density profile, while the cold dark matter models tend to produce a diverging cusp. It's also an explanation why we do not detect dark matter particles on Earth. It is just too light, and the wavelengths too diffuse for Earth to capture any of them. And the particular granularity of ULDM seems to be able to explain why we see fewer dwarf galaxies than the CDM model predicts. In the low energy and stationary background approximation, ULDM simply obeys a Schrödinger equation. It exists as a wave function. This is the point where I would like to revisit what's known as the Mandelung Formalism of quantum mechanics. In the Mandelung Formalism, a wave function is a fluid with its density field and velocity fields encoded in the wave function itself. What happens if we assign to the probability density an associated mass density? And that's the Schrödinger-Poisson system. This modification couples the wave function back to the Schrödinger equation itself in a highly nonlinear fashion. Of course, with this as our fundamental building block, we can add more physical effects in our modeling. Schrödinger-Poisson equations, being highly nonlinear, admits equilibrium solutions called solitons. Roughly speaking, they are the balance states between self-gravity and what's known as quantum pressure. We can radially solve these equations numerically and get their shapes. And we know some scaling laws, that lighter solitons are puffier, they are larger and less dense overall. Here, in both panels, we set up two solitons approaching each other from the same initial location with the same initial speeds. The only difference being the left pair has a non-zero phase difference. As you can see, although each axion particle is gravitationally attracted to each other axion particle, overall, the quantum effect makes the two clumps repel each other, while on the right, it actually facilitates the merger. Let's talk briefly about dynamical friction. It's not a contact force. It's a statistical effect of how a heavy object traveling through an interstellar medium loses some of its momentum and energy. You can think of it as a massive set of gravitational slingshots. We can approach a first-order understanding of dynamical friction in ULDM quantum mechanically. This is the same as the Coulomb scattering problem as you might have encountered in undergraduate quantum mechanics. We work in the particles frame. We assume the effect is perturbative, there's no slowing down. And we assign a 1 over r potential at the particle. As for the initial conditions, we say the axions arrive in a plane wave with uniform velocity and density. If you solve this system, you get a pattern that contains a large overdensity tail that, of course, generates a gravitational pull to the left. There's a problem with this. The overdensity is divergent. It produces infinite dragging force. This is not realistic. People have been proposing a remedy to this problem by saying, we assume the pattern is there, but the interaction was only turned on a finite time ago. That means we only consider what's inside the circle, i.e. impose an infrared cutoff to the integral. With that, you can generate a correlation relationship between dynamical friction force and the system size, i.e. V times t, how long the interaction has been turned on. And that allowed us to set up a first verification run of our code. On the left, we shoot a black hole into a uniform ULDM medium. On the right is the pre-computed final result. You can see as time goes on, the left one approaches the right one. And of course, in our first order consideration, we only solved the Schrödinger equation without Poissonian gravity. In this context, our numerical dynamical friction force agrees with theory quite well. However, you might have also noticed, being an infinite cigar-shaped structure, there's no way the tail is stable under its own gravity. So the first order model isn't correct. We can never reach this state. And that's when we started solving the full Schrödinger-Poisson equation in our code. And you can see, instead of producing just a elongated shape, the tail would actually collapse in on itself, thus dramatically increasing dynamical friction force. With this, we set up a batch of simulations and evaluated the stopping distances, that is how long the black hole would travel before it transfers all its incoming momentum to the dark matter medium. And our result was quite robust across simulation resolutions and system sizes. And this is the point where we briefly touch on our simulation numerical routine. Schrödinger-Poisson, being such an elegantly nonlinear system, has historically attracted interest from both nonlinear optics and fluid mechanics. The Ultralight team took this idea and made a coherent cosmology package. In brief, we couple a reliable frequency space differential equation solver to a series of sophisticated I/O handlers that can generate a large quantity of variables on the fly. Over the year I've been working on this, there were a few verification runs. One of the most important verifications was that our code respects Galilean relativity. That is, you get the same simulation results no matter what reference frame you work in. On the left, a stationary dark matter medium has a black hole traveling through it, while on the right, the black hole stays at rest while dark matter blows past it. That's what we call a quantum wind. In both cases, energy is conserved as well. In the left, you can see the black hole loses all its incoming energy to the medium, while on the right, the medium loses some energy and accelerates the black hole. This establishes the physical relevance and numerical consistency of our simulation code. And here's the main course of today. I'm going to outline our investigations of a toy model where a black hole interacts with a soliton. To get started, here's me demonstrating the effect in person.
I happen to have set up a soliton behind me. Let's see what happens.
And of course, I prepared the same animation in the more traditional top-down two-dimensional view. You can see as the black hole approaches, the entire soliton, the condensate, exhibits highly collective and wave-like oscillations. To make everything more quantitative and graspable, we preferentially studied cases where the black hole initially orbits a soliton in circular orbits and studied how those orbits would decay over time. Here's one of the first results. You can see the infalling time depends quite significantly on the black hole mass, but also the initial radius. With those simulations, we could estimate the time it would take for the black hole to sink to the middle of a soliton. and compare those with first-order estimations using only the Coulomb scattering dynamical friction. They are roughly on the same order of magnitude. However, we also notice some nonlinear effects. For example, you can see on the blue end of the curves, the black hole that initially sinks in the fastest actually gets ejected later in the simulation. We hypothesized that this is because orbital period of such black holes is in resonance with some excited modes of the solitons. So those nonlinear interactions can either facilitate or inhibit orbital decays. In order to study these, we had to implement additional features to pi ultralight. The first one being able to shift into the center of mass frame of any ULDM system, effectively reducing the artifacts associated with our grid-based simulation. On the left is our original simulation in which a soliton travels across the box. On the right is the resampled version where the global phase has been cancelled and it's just a soliton at rest. This works in more complicated interaction pictures as well. Here's one of the orbital decay cases, and on the right is a subsampling of the simulation grid where everything is centered at the center of mass of the dark matter, allowing us to perform more analysis. One of such tools at our disposal, we can numerically solve the Schrödinger-Poisson equation not only for the ground state soliton, but for excited ones. In chemical lingo, ones with more nodes or more lobes, and of course expand those both radially and angularly, and see how different components of our system changes weighting over time. More exotically, we may be able to treat the potential produced by the black hole as a periodic time-varying potential and transform the whole problem into the interaction picture of quantum mechanics. Those work are still being undertaken. For me, computationally, I'm also thinking about moving to more sophisticated tools. Pi ultralight has been a great learning experience to introduce me to the beauty of Schrödinger-Poisson systems. But the numerical performance of Poisson struggles when I try to simulate, say, a galactic core with many black holes, gas, and of course, a larger amount of dark matter. Established solutions in this field exist, such as MREX and NIX. These are adaptive mesh refinement codes. That means as it runs, it intelligently tells which part of the simulation grids needs more attention and solves those areas more carefully. In summary, in this work, we coupled an embodied system to a mesh-based ultralight dark matter simulation. We obtained results comparable to previous work in literature. And this is a direct simulation of the nonlinear effects between a ULDM soliton and a black hole. We have seen some cool dynamics and very complex behavior, even in the simplest of toy models, a single black hole orbiting a soliton. This loops back to my personal motivation in studying ULDM. First is the source of very interesting dynamics. The local effects causes very non-local collective behavior in the condensate. And it's a possible mechanism through which we can bring together black holes, because the oscillations of ULDM may possibly be a mediator between multiple black holes and give us a solution to the final parsec problem. Many of you should know it's that we know black holes merge and coalesce. We don't yet fully know how they find each other to begin with. There's not enough time for our known mechanisms to bring them together. And of course, with missions such as LISA coming online in the next decade, this should be a field of active discussions and debate. This concludes my talk. I would like to thank people at the Department of Physics, University of Auckland, and especially the lovely people of my group for their support and guidance over the publication of my first paper. The computations were performed on on the computers provided by Australian Research Data Commons, and I would like to thank my collaborators both in Göttingen and in Yale. Thank you very much for your attention.